very welcome to our webinar on uncertainties for green hydrogen technologies, a forced technology perspective. We would like to share some quite broad information with you today, and we hope you stay on. So thank you so much for your patience at this stage. Our speakers today is myself and my colleague Ida and my colleague Christian, and we are all based in Brøndby, and then Rian Holstock based in Esbjerg. And of course, we are a Scandinavian-based RTO, but this was just to illustrate that we're quite broadly represented in Denmark also. And a few practicalities today. You probably all discovered that you cannot speak during these presentations because we were close to 100 participants. We may not be as many right now due to the technical issues, but let's hope that more of you will join. If you have any questions during the webinar, we will of course love to answer them, but due to time constraints, this may not be an option today. So please write your name and email and we will follow up on your question. And if you have any wishes or comments for future webinar project content, please also contact us. We were planning on sending out the slides after this. We might be able to add a recording, but we'll let you know. Then we just wanted to tell you that we have a LinkedIn group on hydrogen, handling and transportation that was formed at our very first hydrogen webinar 4 years ago. So that's also a private group to join for discussions if you're interested. And most of you probably already know Force Technology, but just quickly, we are the largest RTO in Denmark. We are independent and self-governing, and we are based in Denmark mainly, but also very heavily in Norway and Sweden. And we provide services to the international market within hydrogen across materials and welding, testing. We have quite large test facilities, fracture mechanics, both testing and calculations. We do flow measurements and simulation. And I can see quite a few of you come from the world of metrology, where we have our large gas test loop facilities. We also cover emissions measurements and on-site inspection and NDT. And then I'll let Ida take over from here.
Yes. Hello, everyone. My name is Ida, and just to give a little presentation of our mini guide within the establishment of hydrogen infrastructure. We have published a mini guide with 4 important aspects. This includes risk assessment, screening of materials, the concept of hydrogen readiness, and that there is a large need for documentation of product regarding performance and safety. And this mini guide can be downloaded on our website, and for now it's in Danish. Let's see if I can move on. So some of these one of these uncertainties could be what should you put hydrogen in before you start to use it. Hydrogen can be a problem because of hydrogen embrittlement. Here you see a fracture, which is fastly propagated. Yeah, I'm sorry, I'm a bit nervous. Hydrogen embrittlement is caused from mainly 3 factors. This is mechanical loading with both residual stresses in the material, operational stresses, and it can be cyclic loading and stuff as well. Then we have environmental impact, which Christian will be talking a bit about later on. And we have the factors from the material itself. This can be the chemical composition itself, inclusions like different contaminating materials, and the microstructure as well. We can get help trying to find out what materials we should use to limit these uncertainties. One of the common standards to use is the ASME B3112. And here we have not a complete list of what you can use and what you cannot use, but only a non-mandatory appendix. Here you can see that there's simplified into acceptable and not acceptable, and sometimes there's a note as well because we lack information. It's very important to look into the most updated version. For example, for this one, there was in the 2019 version for titanium an acceptable evaluation, and it's now changed to not acceptable. So that's a big difference in whether you should use something or not. Just to point out a similar table from ISO 15916. Often we get similar results in these tables. There can be variations which you should be aware of. Things like cast iron is generally not advised for hydrogen service. Sorry. So you can see in these pictures how hydrogen embrittlement or hydrogen environment will have the effect of decreasing the ductility of the material. If you look on the picture to the left, there's this. You can look at it as a warning where the material starts to deform, while on the right side we have a material which has fastly the crack has fastly propagated, and we have no warning signs before cracking. Actually, fatigue crack growth can accelerate up to 10 times compared to non-hydrogen environments. For polymers, we evaluate permeability, diffusivity, and solubility. In the Sandia report, there's examples of a lot of common polymers that has been tested. And one of the failures that you can see is blistering of coatings on metals, for example, due to the flow rate of hydrogen is different in polymers and in metals. So there are these different factors. And in general, these are some things that you need to be aware of when you look for compatible materials within polymers. For polymers, you need to be aware of external factors such as UV, oxygen, heat, and water. And you need to be very aware of permeation as well. Just to point out a few of these points. Now, you will have to go through evaluation process in order to both design and in order to repurpose materials and components for hydrogen service. And I think that it's especially interesting to point out the part where you have to consider if you have made changes to the environment, or do you need to make modifications or not. And I think Rian will talk a bit about another part of this later on. For components, there is a similar way to get help from documentations. This is from Marcogas, a publication made on hydrogen used in existing infrastructure for oil and gas. And for this example, we have a pipeline for transmission, where the corrosion protection is similar for hydrogen service, or shouldn't be too much adjustment for that. On the other hand, if we look at valves, we need to make big adjustments. So, yeah.
I'll shortly now talk about some of the uncertainties that arises from gas purity and the effect on hydrogen readiness. A bit of short introduction. My name is Christian. I have a background as a material chemist, so it's a bit more of a chemical perspective on the issue than you might be used to. Let's see if this works. Now, from a gas purity perspective, what is hydrogen readiness? Well, in my opinion, being hydrogen ready means knowing what hydrogen quality you will need for whatever system you're operating, and what quality of hydrogen you will receive. Those two aren't always in alignment with each other. You might expect to receive 100% pure hydrogen, but in all likelihood, you probably won't. This is largely due to the fact that impurities are introduced during all stages, from production to handling, storage, and even from the infrastructure itself. Of course, it could be expected that the initial purity you will receive is different from the purity you will receive when the technology has matured. A simple reason for this could be that at the moment there's no dedicated infrastructure. You will be using refurbished pipes, where it can be expected that some amount of impurity will leach from. Additionally, the local infrastructure and handling and storage also contribute to impurities, and as such, you can't expect the impurities in one locale to be the same as in another. So expect variations depending on the local environment that you're in. Also, depending on if you're using refurbished pipes, the quality of in this case, natural gas that you were receiving before, that can have an impact on the quality and the presence of certain impurities in the hydrogen you will receive in the future. Now, hydrogen has several different use cases. One of the more simple ones is using it simply as an energy source for heating. You might assume that this means that you don't have to concern yourself much with the impurities in the hydrogen. You could maybe get away with not processing the hydrogen you receive further, because, well, as long as it has the correct amount of energy, as long as the Warp index or the output of the combustion is within your accepted range, you might assume that this is perfectly fine and you need not worry, unlike other industries where the hydrogen they receive might need to be purified further before it can be used. However, depending on what impurities the hydrogen gas contains, you might need to consider if some form of cleaning or scrubbing is necessary. One could expect the presence of sulfur compounds or ammonia, small traces of ammonia or sulfur compounds, which might, in the case of your system, provide some long-term risks that might not be initially sort of clearly visible in the short term. So you should consider if the purity of hydrogen that you will receive, is that adequate? Do you need to purify it even if you just need to use it for heating? Now, if you go the step beyond and go to higher purity of hydrogen, the individual impurities begin to matter a lot more, because two impurities might result in radically different effects on your material. And this is also depending on the two sort of primary issues with hydrogen, which is the hydrogen embrittlement and the fatigue crack growth. And different impurities have a different effect on either of the two. So if we begin with looking a bit at the fatigue crack growth, we have quite a solid understanding on the effects of, for instance, oxygen and carbon monoxide that would be present in the hydrogen. Both of these seem to inhibit the fatigue crack growth, even in small amounts, as can be seen on the figure on the right, even at the 0.1% of a percent. No, sorry, 0.1 of a percent. Oxygen has a large impact in reducing the susceptibility of the steel tested for fatigue crack growth. The exact reason behind these are a bit more complicated, but in short, as far as theory goes, it prevents dissociation, and as such prevents the hydrogen from entering into your material. Other known effects are the sort of more damaging effects of hydrogen sulfide and methane thiol. These, as you can see on the furthest right on the figure, even in small quantities, for instance, hydrogen sulfide is quite damaging when compared to just pure hydrogen atmosphere. And adding to this, there is quite limited understanding then of a lot of other impurities effects, and even more so when you start to consider the interplay between different impurities. The figure, as you can see, displays that carbon dioxide and water have slight detrimental effects, which is still up for debate if that is the case or not. Different papers disagree on it. But what about the interplay between the two? Think, what does carbonic acid do? You dissolve a bit of carbon dioxide in your water, now you have carbonic acid instead. How does that impact the material's resilience to fatigue crack growth rate? This is not even to touch on system-specific factors where the picture becomes even more complex. Effects such as pH, temperature, the presence of chlorinated compounds, certain microbial effects, the pressure of the hydrogen you're working with even has an effect. As an example, the figure on the right, you can see a rough evaluation of nickel-containing alloys in a high temperature and highly alkaline environment under the presence of several bars of hydrogen pressure. In this case, you want a higher nickel content to increase the corrosion resistance in the alkaline environment. However, as your nickel content increases, so does your susceptibility to hydrogen embrittlement. So there's a small Goldilocks zone where you maximize your corrosion resistance and minimizes the risk of hydrogen embrittlement. And further adding to the complexity of a situation like this, what is the strain on individual components in the system? What about system-specific operational conditions, start-stop procedures? It quickly becomes quite complex as you introduce further aspects. And unfortunately, reality is quite complex, and you often don't have a perfectly sealed environment. So this brings me back to my original statement, which is what hydrogen readiness is from the gas purity standpoint. You need to minimize these uncertainties, so at least minimize uncertainty with the gas you will be receiving and the gas that you want to receive. Know what you will need to receive and know what you probably will receive.
Thanks, Christian. I'm just sitting in a different location. I'm going to see if I can manage technology here. But before I start, I've got a laptop and I've got a monitor. So I'd be looking in both of those. But if I look like this, I'm looking at my laptop. And if I'm looking like that, I'm looking at my monitor. So forgive my head moving left and right. So let me share my content. Ready for hydrogen, as Christian said. I think what we need to do is, first of all, look at some definitions. Share my screen. Let's go there. Right. Just a quick sanity check here. Can you, Christian,
Looks
can you
good.
see? It's
Looks
working.
good,
I
Wayne.
can see.
Yep.
Perfect. All right. First hurdle taken care of. As we can see, this is just a start. Christian has already told us that there's one definition of readiness, and we've got how many? 6 or 7 listed here, but there are several definitions of hydrogen readiness, and it all depends of our angle and where we come from. Even legislation. Is the system, is the component, is the device, is the material, does it comply with some of the EU, and in this case we're talking EU legislation. It could be the vocabulary, it's the terminology that we're using for the system, the terminology we're using to describe the system. Is it the same? Traceability, and of course here we have with green hydrogen, we have the origin, certificate of origin. Is it green hydrogen that we're dealing with? Measurement. We have some challenges measuring hydrogen accurately, and we are still also not 100% sure about those measurements over long term. Purity, as Christian just spoke about. Of course, the other hydrogen ready definition is marketing. If I have a product that I want to market, I want to sell, I want to be able to claim that it's ready. But what is it ready for? So this is probably where we start with or we continue with the uncertainty. Is we need to understand what is it that we are looking at, what is it that we mean. Is my reference point for hydrogen the same as your reference point? That's the first thing we need to establish. So let's look at slide number 2. To help us, we can start with 2 words here: compatibility and suitability. Now, compatibility gives us a general description of whether there is some history, some experience with the material. Let's use material here as an example, like stainless steels or austenitic stainless steels. We know that austenitic stainless steels, as Ida has shown us earlier, could be okay generally, but there are also instances where the austenitic stainless steels will not be okay. So we now have to introduce a different word called suitability. So suitability means that the component, the materials, the system has been evaluated under very specific conditions. So that would normally be your operating conditions, and your operating conditions today, but also your operating conditions in 5 years' time. So we need to be aware of the application, what will change, and how is the system going to change. So those changes become part of the test parameters, part of the evaluation. So normally we do a short-term evaluation and a long-term evaluation. Short-term evaluation, as an example, is, does the thing leak? And a long-term evaluation is, all right, once we add hydrogen in there under different cyclic loads, different temperature fluctuations, maybe even different purity levels, 6 months, a year, does that have an impact, an effect on the system? So to help us here is, if I want to sell something, I could say, look, it's compatible. But if I want to then use it for something specific, I need to do a bit more work. I need to find out if if suitability has been established, and that means, has it been tested? Has it been evaluated for the conditions that it would be used in? Right, and just to give an example of a valve here, these are some of the things to consider. Of course, we can start a desktop study with the general compatibility of materials. And once that's established, so that's your screening process, then you dig a bit deeper and to look at the uncertainty, to see how much of it has been taken care of. Look at the fracture and fatigue data. Has it been tested in the conditions that it's going to be used for? Does it include the pressure cycling, the temperature fluctuations, even the rapid decompression that we're expecting or may have in the system? This is for a pressurized pipeline system, but it could also apply to other hydrogen technologies. And with the attics and explosive considerations, even ignition sources. So there's a lot to look at, and a lot of this gives us uncertainty because it's quite specialized, and we have to consider many things. Now, that's what we're going to look at now is this traceability. What do we look at? What sort of evidence do we need to gather? How do we do that? And within the next 5 or 10 minutes, we cannot tell you everything. It's the field is very big, but what we can do is we can hopefully just turn on some lights just to show the sort of the path, the direction that industry is taking at the moment, that it is following. And traceability is certainly one of the buzzwords. What we see here are some documents that we've been working with. There are many more, and a lot of publications now. And this is making it even more confusing. Where do we start? What do we look at? We do have a baseline that we can work from. And the typical route is in the European Union is this CE marking type route, where we look at the EU directives, we pick out the harmonized standards, we work according to those harmonized standards, we then compile the technical documentation, we then do a conformity assessment, and the conformity assessment should then show that, yes, it's followed the rules. And once all those rules have been followed, it gets a tick in the box. That's the typical route. So we'll use that. We'll use that as the baseline. We'll stick to that. But we have something new. We've got hydrogen now, and of course hydrogen isn't new, but in the scale that we are going to make hydrogen and to store it, transport it, and use it, that changes things a little bit. Okay, so my Bible here is something produced by the European Clean Hydrogen Alliance, and it's a group of industry members, and they've been tasked by the European Commission, the European Union, to go and do a study on where are we in terms of the standards, specifications for hydrogen in the European Union. Where are we? So they've spent 3 years studying this. They released this document a year ago, a little bit more than a year ago, March last year. They looked at 400 topics in the hydrogen value chain, and they found where the gaps are. And they also said, look, according to the European direction, these European regulations like Repower EU, to be energy independent or Fit for 55. They said, where do we need to go? And to be able to get there, what do we need? They've also worked with ISO. So this is SCN and ISO working together to make sure that what we do in Europe is not standalone. But they've created this document called the hydrogen roadmap or the roadmap on hydrogen standardization. It's freely available. So I would advise, recommend you to just do a search for it on the internet, the roadmap on hydrogen standardization. For me, that's my Bible that I'm working with. And it's looked at where we are in Europe and said, okay, we have a bit of a challenge. About 80% of what we need is there, but there's 20% that we need to work on. And this is a snip from the roadmap. As we can see there, there's approximately 7 years where we need to develop, define, create, edit things. So there's going to be a time of uncertainty, approximately 7 years, where not everything is going to be in place. So we need to start thinking about alternative ways, alternative to the normal way that we've been working. And why it's a nice Bible or a nice reference, because it's very specific. It's got hundreds of these standards that we work with, that we use as evidence to say, here, I'm using this standard, I'm fulfilling the safety requirements from the European Union, therefore everything will be fine. But we can see now, here, just 3 examples here. There are many, many more. We can see there's to be on the right-hand side here, there's to be identified, there's under revision, and there's also in preparation. So they tell us, the roadmap tells us, for a specific standard, for that hydrogen technology, where are we? And it gives me as a decision maker, it will give me an idea of how much effort I need, how much additional work do I need, to be able to show that something is ready, to be able to show that, all right, I've taken care of the uncertainties. Okay, so remember previously we had a similar slide. What is different now? Let's call it the modified route. And this is something that we've seen being used across Europe. This is not just something from Force Technology. Is that there's a bigger focus now on the risk assessment. So we use the system that we had previously before hydrogen, or before this mass introduction of hydrogen. What we need to do now is we find which of these harmonized standards that we normally would need are not in place, that are not there. Then we define activities to substitute for those standards. Like we do some additional testing, short-term testing, long-term testing, fatigue testing, rapid decompression testing, whatever the risk assessment tells you is the big risk that you need to focus on. We then define activities for that. And we do the evaluation, we get the results, and if those results show you that we are taking care of the risks that have been identified, we are managing those risks, we then start compiling our document package. So that is really the new thing, and the key part of the new documentation strategy is we have to spend more effort now to find out, okay, where are the big risks? Do we have standards, harmonized standards that we can use? If we don't, we need to then define activities, generate the evidence, put that evidence in a document package. That document package is then a modified document package, because some of the things you would do is you would use non-harmonized ways to do things, and there are several ways that we can do this. But the philosophy, the intention would be you need to show that you're managing the risk, and that will give you your document package and your traceability. And as I said, there's a lot to cover, and we won't be able to do everything in the session that we have. But just to give you a snapshot, we have got processes that we can inherit from, let's call it pre-hydrogen days. And Ida showed one earlier here's one from iGEM. We have processes that we can follow, and it's just here on the right-hand side where there's a quantitative risk assessment, the QRA, that needs to be modified and that needs to be a bit bigger now. We need to focus more, find out really where these risks are, the bigger risks are, and what activities can we generate to show that we are managing these risks and that we also have traceability to show what we have done. And that seems to be the general approach that we're seeing within the world, specifically within the European Union, but how we are dealing with documentation for the Power-to-X, the new hydrogen world. I think that is, yes, that's my last slide. So I'm going to hand you over to Dieter now to tell us a little bit about some other things.
Thank you, Ian. So sorry for expanding these uncertainties. We would love to provide all the answers, and of course we can provide some answers. But the purpose of today was also to put the spotlight on where are the gaps, where do we need more knowledge, and how can we assist you in this. But how do we close the gaps on these uncertainties? Well, one way is through standardization. In the standardization world, we're converging to obtain some uniformity in standardization. Of course, traditionally, there's always been a difference between Europe and the US, but there's a general consensus on most things. And at Force Technology, we also participate in standardization on a national level, and we follow relevant international standardization. And it may be a jungle and a lot of documents, but we are trying to keep track and it can, of course, assist you. But just to list some of the important updates to follow, like Ida mentioned, the S&P 3112, a recent version was released just around the new year. There's definitely going to be more development in that area, and it's the go-to or main standard being applied internationally at the moment. But we also have a lot of guidelines, the IGA, the European Gas Association, and the British version, the IGEM. Then for components, we get a lot of questions because it's not just about the single materials. What if you put them together? And what about the non-metallic materials? As Ida mentioned, that's a whole different world. And you have a higher risk of leakage through these gaskets and O-rings and assemblies. There's going to be a recent update on the valve standard for hydrogen service. Also, the NACE MRISO 15156, which is intended for sour service hydrogen sulfide, where you have a lot of hydrogen entering the steel. It's generally considered conservative. So the list of materials allowed in this is at least considered a conservative approach if you apply that for Power-to-X or dry hydrogen gas. But there's also development in that area in terms of discussion of hardness limits and so forth. Then across the border in Germany, we have DVGW with a lot of guidelines, also in line with most international standards. And then in the ISO world, we have the 880 for refueling stations, because of course, hydrogen is not new and it has been out there for a while. It's being managed at high pressures, so that also provides some guidance. And we have Sandia National Laboratories, other test institutes. But again, in a few years' time, we will be a lot closer to providing more specific answer. But in order to get there, we also need to close the gaps by testing. We hear a lot that test results are needed as input for standards. And right now we have no single harmonized way of testing for hydrogen compatibility or suitability. We still have a lot of uncertainties in evaluation of the most suitable test method. That could be, well, as Rian mentioned, what is short-term testing? What test pressure, what holding time? How many cycles is a fatigue test? What is considered long-term if you want to assess the lifetime of a component? And the blue image is a recently installed component test rig that we have here at our facilities in Brøndby, where we aim at supplying some of these answers. Then on the international scene, a correlation between testing in hydrogen gas, which requires a lot of safety in the lab laboratories, substituting that to electrochemical charging in a liquid, which is just basically salt water and photentiostat, would make it a lot easier, faster, and cheaper. But you need to have a correlation between the electrochemical potential and the partial pressure. So that's also something still explored. And looking at fracture mechanics, just assessing which method is the best. You have huge discussions going on ASTM E1681 versus E1820. We will be able to supply testing according to one for the moment, but that's also being discussed internationally. And acceptance criteria and how to evaluate specimens after a test even differs across test laboratories. So there's still a lot of uncertainties just within the world of testing. And the hope is that we get to a point where extensive testing is no longer needed because we know a lot more. And you may know that we have test facilities both for testing of hydrogen compatibility, sensitivity of material, also permeability, because we get a lot of question, well, does the hydrogen even enter the material and at what rate? So we also have the option of testing barrier effects of coatings and so forth. And in our recently installed hydrogen autoclave, we can do fracture mechanics testing up to, at some point, 500 bars. We're starting lower. And the test rig I just showed you before will be able to handle large-scale component testing. So we have a lot of options. I know we're running out of time, so we just wanted to know that let you know that another way of closing the gaps is to interact with you in industry through research and development projects. And current projects are across a wide range of topics, documentation demands, testing, how to set demands for hydrogen compatibility, safe storage, bunkering, and utilization of green fuels, electrolyzers. And Christian touched upon hydrogen purity. We have a current project, which is also open to new partners. And within carbon capture and storage, we also have similar facilities and options as for hydrogen. So please get in touch with us for future project ideas and collaboration. We would love that. And I will just skip this one as an example. And just sum up that we really want you to have all the answers, and please get in touch with us. This was a way of touching upon some of the uncertainties, and we are working to close the gaps on these. And one of the ways was to make this small mini guide that hopefully provides some of the answers, and then you're always welcome to get in contact with us and keep an eye out for any news from our side. So thank you so much for today, and I know it's 2 o'clock precisely. And please email us with any questions. Last time I checked, there weren't any questions in the chat, but we will keep in touch and look forward to hearing from you.